welcome to today's webinar, Introduction to Docker on AWS. Our presenter today is Brandon Chavis. Brandon is a solutions architect at AWS. He specializes in high-scale container orchestration and application management, distributed storage systems, and fault-tolerant database design. He has helped customers around the world build well-architected and cost-effective solutions on the cloud. He currently focuses on enabling partners in the container ecosystem to build stronger products and better leverage cloud technologies in their designs. Today with us, we also have Daniela Strapa, Solutions Architect at AWS, and Andrew Thomas, Senior Product Manager for ECS. Daniel and Andrew will engage with you and answer your questions throughout today's presentation. Now, Brandon, welcome. I pass the floor to you.
Thanks, Bowen. Welcome, everyone. Thanks for joining the webinar today. Coming to you live from beautiful Seattle, Washington, where it's currently cold and overcast, but not currently raining sideways, so we'll chalk that up as a win. Today we're going to talk about Docker on AWS, and so the content that we have for you today is applicable for you if your comfort level with Docker ranges from what is it to I've already thought about Docker and I'm comfortable with it and I want to start using it on AWS. So hopefully we have something for everyone here in the webinar, and let's go ahead and get started and talk about the agenda. So we're going to talk about why you might want to use containers. We'll understand what they're for, how customers are currently using them, and then we'll talk about how you can use containers at scale on AWS. We'll talk about a service we've built called Amazon ECS. That gives you some cluster management functionality, some benefits of this service, and we'll talk about how you can put all this together by running services on top of Amazon ECS. And then at the end, we'll do a live demo. We've prayed to the demo god, so hopefully that works well for us. And we'll kind of show you how both the Docker CLI and the ECS console will work together. So first, as I mentioned, we'll talk about why you might be interested in containers. So containers are very similar to hardware virtualization, like with EC2, but instead of partitioning a physical machine, containers isolate the actual processes running on a single operating system. So to do this, Docker leverages some features in the underlying operating system kernel to create multiple isolated user space processes, and you can place constraints on these like CPU and memory. You can also prevent a process, for example, from seeing a file system or components in the file system that you don't want it to see. And so on top of this, the Docker CLI kind of harnesses all of these features, and the Docker CLI really makes it easy to use containers, and they provide a bunch of commands that make it really intuitive to spin up containers and interact with them. Docker also provides like an imaging system, so it makes it very easy to define what runs in a container and what version of your application runs in the container. And all these things together really enable automation, so you can define your application, you can build and share the image, and then ultimately you can deploy that image in a repeatable way. So you might be thinking, you know, that sounds pretty interesting, but why would I want to use containers? I can do kind of a lot of this with virtual machines already. But we've identified, 4 key benefits to using containers, and the first is that they're very portable. So that image that you build with the Docker interface is very consistent and immutable. So no matter where you run it, or when you start it, it's the same. And this makes the development life cycle a lot simpler. So an image works the same on your local developer desktop or in your production environment, whether you start it today or you scale your environment tomorrow, and there's no surprises in the functionality of your application. And that entire application is self-contained, so the image is the version, and that makes deployments and scaling easier because it's very easy to roll back or upgrade, and that image includes all the dependencies. There's also a lot of flexibility you get from using containers. So you can create clean, reproducible, and modular environments. So in the past, you'd probably have multiple processes running on the same OS, right? So you'd have your application, maybe a caching layer, something that does log pushing. But now with containers, you can really decompose that application into smaller chunks. And there's an application or an architecture called microservices that reduces complexity and lets teams move a lot faster that containers really enable. And we'll talk a little bit about how that works. The end goal here, though, is you really can reduce interdependency of different components of an application, do things like limit library conflicts. So it can streamline both code deployment and infrastructure management. And so containers are also fast, both in the speed of starting up a container, but also in that it allows you to move quicker in terms of application development and deployment of that application. So containers start quickly because the underlying operating system is already running, but each container can also be a single-threaded development stream with less interdependencies. And so we found that ops teams and development teams both benefit from this speed. And finally, containers are really efficient, so you can allocate exactly the resources you want, right? So specific CPU, RAM, or network, right? And so since that container shares the same operating system and libraries with other containers running on the same host, it really uses less resources than running a virtual machine. It doesn't require a full operating system underneath on top of a hypervisor. So to support that notion that microservices are actually beneficial in terms of helping you scale better, helping you move faster, I have a little bit of a story about an online retailer called Amazon.com. And I hear they're a fairly large organization now, running a pretty big e-commerce site. So about 10 years ago, this Amazon.com had a large monolithic application running its website. So everything from the UI, the ordering systems, the recommendation engine, the shopping cart, this was all one large code base, one monolithic application. And the problem was that there were a lot of code interdependencies between all of these different components. And this made it hard to scale the website. So if one service was memory intensive and another was CPU intensive, the servers really had to be provisioned with enough memory and CPU to handle that baseline load. So if the CPU intensive service had received a heavy load, you have to provision a lot of machines and have a lot of underutilized resources. So in order to scale better, Amazon decomposed the architecture into individual services that could be deployed separately. So this allowed each service to scale independently. It was able to have, it enabled smaller teams to work on each of the services, and each of those teams controlled a different code base for that service. So this allowed the website to evolve faster because new updates can be delivered independently of other teams. And this is the architecture now that we call microservices. And so containers are really natural for this pattern of microservices. It really makes it simple to model. The application and all the dependencies are packaged into an image using a Docker file. And that supports any application, any language. And that image is just a versioned artifact that can be stored in a repository just like your source code. But this makes applications easy to test and deploy because they are the same artifacts. Containers also really simplify deployment. You can build stateless servers, and that's a really natural pattern with Docker. And that means that each deployment, each upgrade would be a new set of containers. Another benefit is that really reduces the risk of changes. So rollback is simple. You can just go back to a previous version. And all these things rolled together really make it easy to decompose an application into microservices. The end goal really is reducing dependencies and to decouple components of the application. So when you're using Docker, as we'll demo later, the CLI is really intuitive. It's great to go from just some source code and a Docker file to a running image. And so it's really intuitive, especially when you're just in the development workflow, you're running a single container on your laptop. But when the amount of containers you're running starts to look like this, well, chances are you're running a cluster, and cluster management is really a non-trivial task in most cases. So you need a way to intelligently place your containers on the instances in your cluster that have the resources that your container is going to need. So in order to do that intelligently, which is the key word here, you have to know the state of everything in your system. So for example, what instances are available and up and running in my cluster, and which one of those have available resources? How do I know if a container dies, or how do I hook up my containers to other AWS resources like ELB? Can I extend to things that I already use, like a CI/CD pipeline or maybe a third-party scheduler? And these are a lot of questions that our customers had asked us. So some of these challenges are what led us to actually build ECS. So I talked a little bit about cluster management. Let's look into that some. One important component of cluster management is having a resource manager that's responsible for keeping track of all your resources naturally. To properly schedule, you need to know some things about your cluster. So you need to know constraints like memory and CPU. You need to find resources in your cluster that meet the constraints. You then need to request the resource that you want. Then the state manager on the back end has to confirm that that resource is available. And so the scheduler is really responsible for the whole. If that task is alive, or if it's dead, what should then happen with it? Should it reschedule that task? Generally the answer is yes, but the scheduler gives you control over such things. So moving forward here, if everyone's looking at the slide called Amazon ECS Resource Management, I'll start talking about that now. So ECS provides one solution for cluster management. So basically we have a cluster management engine on the back end that coordinates the cluster of EC2 instances, which ultimately in cluster form is just a pool of CPU, memory, and storage. And so these are EC2 instances that are running our ECS agent. And that means they've been checked into a cluster. So you own these instances, you can SSH into them if you want, and this cluster is dynamically scalable. It's possible to have a 1-instance cluster, or even 100 or 1,000 instance cluster. Generally, customers use clusters as kind of a placement boundary, or a boundary for different purposes. So you might want to segment an application based on the scaling needs, for example, or based on security needs, or for totally different environments, so like a development environment or a production environment. You might use different clusters for these. So I mentioned the ECS agent, and this is a piece of code that runs on each instance, and basically that handles communicating with the backend ECS engine, and then it processes ECS commands and turns them into Docker commands. So it binds locally to the Docker socket. When you make an API call to ECS, it is then forwarded to the agent running on all of the instances, and then that command is basically processed and parsed and fed into the Docker daemon to then run containers locally on the instances. This agent is open source. It's written in Go, and it's available on GitHub. And we like to develop it out in the open. So we really like to see feedback on that process, right? So we like to see if there's any changes that should be made. We're always looking out for pull requests and ways that we can improve things. So let's talk a little bit about the nitty-gritty behind ECS here, right? So to coordinate this cluster, we need a single source of truth for all the instances in the cluster, all the tasks running on all the instances, the containers that make up the tasks, and the resources that are available. And so all of this rolled together is known as the cluster state. At the heart of ECS is a key value store that stores all of this cluster state. In order to make this robust and scalable, this key value store needs to be distributed for availability and durability. But because the key value store is distributed, making sure data is consistent and handling concurrent changes becomes a little bit more difficult. This is a challenge amongst distributed systems in general. So as an example of this challenge, if two developers request, for example, all the remaining memory from a certain EC2 instance for their one container, only one developer's container can actually receive those resources, and the other would have to be told that their request could not be completed. So because of this, we need some form of concurrency control, and that has to be put in place in order to make sure that multiple state changes don't conflict. So let's talk a little bit about how we actually achieve this concurrency control under the hood. This is a very simple example, but we implemented Amazon ECS using something kind of complex, and it's a core distributed system primitive that we use internally at Amazon. And it's a Paxos-based transactional journal that keeps a record of every change made to a data entry. A little bit more. And so any write to this data store is committed as a transaction in the journal with a specific order-based ID. And so that current value in a data store is the sum of all transactions made as recorded by the journal. And any read in the data store is basically just a snapshot in time of the journal. Now, for a write to succeed, the write proposed must be the latest transaction since the last read. So what does that mean? So if a user made a read and subsequently a few writes happen after that read, and then the user tries to write based on the last seen ID, the write wouldn't succeed. Right? So you need to know the latest update to the journal in order to make an append to it. So this primitive allows ECS to store cluster state with optimistic concurrency. And so that's ideal in environments where constantly changing data is shared. And this architecture affords ECS high availability, low latency, and high throughput because the data store is never pessimistically locked. Another unique thing about ECS is we decouple the container scheduling from the cluster management. So we've opened up this cluster manager that I just described through a set of APIs that allow customers to access all the cluster state stored in that key value store. So this set of APIs form the basis of solutions that customers can build on top of ECS, such as connecting your CI/CD system or additional third-party schedulers, custom schedulers, for example. So a custom scheduler, for example, a scheduler, again, just provides logic around how, when, and where to start and stop containers. So our architecture is designed to share the state of the cluster and allow you to run as many varieties of schedulers that might do different things like bin packing, or maybe they have a spread strategy. So as many schedulers as you need for your application. Other applications can hook into this as well. So when you have the full state of the cluster available via a few API calls, you can really make informed decisions on how you should interact with your container infrastructure. So a little bit more about scheduling. With ECS, each scheduler periodically can query the entire cluster state, and it can do so to check the resource availability. So to schedule a task, the scheduler makes a claim for any available resources that the backend APIs say are available. The scheduler will then update the cluster state when the newly claimed resources are actually claimed and held by that scheduler in an atomic transaction. So it will then update that key value store on the backend. If a resource is already claimed, though, ECS will reject the transaction because it maintains that concurrency control. So what ECS enables is called shared state optimistic scheduling, where all the schedulers can see the current state of the cluster at all times and not just specific offers that the cluster thinks that scheduler might need. So that sounds awesome, right? But what are the actual benefits of this? What are the benefits of ECS? We developed ECS because customers had been running containers in Docker on EC2 for some time, but customers told us that there was some difficulty of running containers at large scale, which generally involved installing and managing some sort of cluster management software. And so we're able to eliminate cluster management software. We can manage the cluster state for you. We can manage containers. We can provide enhanced control and monitoring. And we can help you scale from 1 to tens of thousands of containers using Amazon ECS. Earlier this year, we ran a load test just to see how well this functions. And so over a 3-day period, we scaled the cluster from 200 to over 1,000 instances. And that's represented by the purple line on this graph. The green and red lines show P99 and P50 latencies. So as you can see there, they're pretty flat, which demonstrates that ECS is pretty stable and it scales regardless of your cluster size. So that's good when you have that consistent, predictable performance, no matter the size of the cluster that you're running. We've also provided 2 built-in schedulers to help you find the optimal placement based on your resource needs or isolation policies or availability requirements. And those 2 schedulers are a scheduler for long-running applications and services, and then a scheduler for short-running tasks like batch jobs. So as discussed before, because ECS provides you a really powerful set of APIs, it allows you to integrate your own custom schedulers as well as any other open source schedulers that you might want to use. So flexibility is one of the #1 advantages of using Amazon ECS in this regard. On top of this, though, ECS is built to work with the AWS services you probably already use. So you can set up each cluster in its own VPC and use security groups to control network access to your EC2 instances. You can store persistent information using EBS, and you can route traffic to containers using ELB. CloudTrail integration, for example, will capture every API access for security analysis later. It can do resource change tracking and compliance auditing. So using all these things together on top of ECS provides a very complete solution for container management. And so the APIs that we provide, so similarly, if you're familiar with EC2 APIs, you'll probably find that ECS APIs are very intuitive, very comprehensive. You'll find things like list and describe and run APIs, which probably sound very familiar if you're using EC2. So you can connect your own scheduler or connect ECS into your existing software delivery pipeline. So all of this is really afforded by these APIs. Another component of our extensibility is that our container agent and our CLI are open source and available on GitHub. And so if you were so inclined, you could modify these to work with whatever application you were looking to use on top of ECS. So to sum up everything, what ECS allows is the reduction of the amount of code that you need to go from idea to implementation when building distributed systems. So rather than having another cluster management software that you manage in order to manage your cluster, ECS manages that for you. You basically bring up an instance, you check it into your cluster, and then it's available to be interacted with via a set of APIs. So it's a lot of that undifferentiated heavy lifting and housekeeping that's been abstracted behind a set of ECS APIs. The ability to run multiple tasks on shared pools of resources can also lead to higher utilization and faster task completion than if different compute resources are statically partitioned. So we've talked a lot about services. How does that work on Amazon ECS? You can model your application using a file called a task definition, and this definition defines the containers you want to run together. So a task definition allows you to specify Docker concepts like links to establish network channels between the different containers and the volumes your containers need. Task definitions are tracked by name and revision just like Docker containers themselves or like your source code. But the key thing to remember is that if you need multiple containers to work together as components of an application and they should run together on the same instance, you would define them in a task definition together. So to create a task definition, you can use the console to specify the Docker image to use for the containers. You can also specify resources like CPU and memory, ports, volumes, etc. for each container. And you can specify what command to run when the container starts up. Then the essential flag basically specifies if the entire task should fail if that essential container stops running. You can also type everything as JSON if you want. We also have a CLI that supports Docker Compose format, so you have some flexibility in how you actually construct your task definitions. So once your task definition is created, you have that JSON file all finished. You then schedule that task definition onto an instance that has available resources. So once you schedule that task definition, it becomes a task, a running version of that task definition. And a task is, as I said, just that instantiation, but it's the core unit of work in ECS here. And so you can have a task that has a single container or up to 10 containers that work together on a single machine. So as an example, maybe you have an application that needs Nginx, Rails, and Redis all running together. You could define all three of those in the same task definition, and when you schedule that onto an instance, those will all come up together. And so you can run as many tasks on an instance as will fit. You just have to watch out for your resource utilization like memory or CPU before more instances are needed in the cluster. So you might be wondering about cross-host links. As I mentioned, you can do local container links. Those wouldn't go in your task, but you might put tasks behind an ELB, for example, and use an ELB to make calls between those services. Alternatively, you might use a service discovery option, and we have a variety of partners that provide that sort of functionality that we can talk about later. So here's where you actually create a service. And this service scheduler is good for long-running applications. And so when you create a service, you reference a task definition and then the number of tasks you want to run. And then optionally, you can define an ELB. So the scheduler will launch the number of tasks that you requested. And once it's brought those tasks up, it always attempts to maintain an equilibrium. So in order to maintain the number of tasks you want, it functions similarly to an autoscaling group. It has a desired capacity. It always makes sure that it has reached that desired capacity. And for example, if one of the tasks are terminated or it fails or the underlying instance fails, the service scheduler will make sure that it again adds another task in order to reach that equilibrium once again. And so with the service scheduler, we have APIs that allow you to scale the service. So you can tell it to scale up, you can tell it to scale down, and you can do so programmatically based on alarms should you need to. There's also an update service API, which allows you to do things like roll out new versions. And there's a lot of flexibility in how you deploy new versions of applications. We give you some parameters that allow you to determine what's the minimum amount of containers that should be running and what's the maximum amount that should be running during a deployment. So are we allowed to kill all of the tasks at once and deploy a full new version, or should we do a gradual rollout? So if we do a gradual rollout, we'll gradually drain connections from old containers and remove the containers as they're no longer serving requests. And we'll only leave the newest containers running. So we've talked about a bunch of things with ECS here. Let's go ahead and switch over to the demo and get our hands dirty with some Docker and some ECS. Cool. All right. So hopefully everyone can see my terminal. Everyone can see Chrome in the background here. So we have a source code repository here. This is our sample PHP app. And so maybe we'll start by just getting some source code to start working with. So we'll go ahead and grab this and pull it down. Great. So we'll see what's inside this repository. We have a Docker file, which we should take a look at real quick. So as we can see, this is just a declarative format that tells Docker what to do inside the container when we spin it up. So maybe some of the interesting components of this are we have a from command, which specifies the base image we're going to use. And so this Ubuntu 12.04 image is just available in Docker Hub. You could go to Docker Hub and you could search for a variety of different containers. You'll find things like pre-built Apache or Nginx or Redis containers in Docker Hub, and you can start using those as functional baselines for your application. There's also much more simple stripped down containers that exist, like Alpine Linux, for example, just the bare minimum needed to maybe run a Go binary, for example. So after that, we're doing some things inside the container. We're going to run apt-get update, apt-get install. Because this is an older image, that apt-get update takes quite a while. So be cautious of what you actually do inside of your Docker file. Next, we're going to install an application. We'll configure Apache, and we'll expose port 80 at the very bottom. Last, there's a CMD, the command that specifies we're actually going to start up Apache in detached mode, and that way we can start serving our application as soon as the container spins up. Another thing I want to show is Amazon EC2 Container Registry. So before I build a container, we need a place to store it. So we could use Docker Hub. We can also use ECR. What we're going to do real quick is just create, let's do this demo app. Make it shorter, and we'll create this repository. So I've successfully created my new repository. And in order to start using it, we need to first get the login credentials in order to use that. So back to my terminal here. Let's get my login. Whoa, what happens? We return a string that you can use, which is literally just a Docker login command with a hashed credential. So we'll just run that real quickly. We'll see login succeeded. I'll clear that off. And now I can interact with my Docker repository. So now we need to build the image that we have, or the image that we want to use. So I'm already in this directory, right? And I already have my Docker file locally. So we can run this command and specify with the dot that we're going to build the container in the current directory. So that happened really quickly, and my secret is that I actually built the container before the webinar because not everyone wants to watch apt-get upgrade complete inside the container. So we can look, Docker images, we can see that I have a container here. It was built yesterday, but this is our demo app right here, 262 megabytes. Resize this a little bit. There we go. Awesome. So what do we need to do to actually push it to the repository? We're going to tag it with the demo app name and the latest version, and we're going to push it to our repository. Right, so we'll tag that, and we can see Docker images again, that now it is tagged with this repository's information. And finally, we can push this up to ECR. So let's get that going. While that's actually working, we can talk a little bit about ECR. My webinar software overlaps with my done button. There we go. So with ECR, we can see that it will show us images that exist once we've pushed some to it. We can also configure permissions for ECR. One of the great things about our container registry is that you can authenticate using IAM permissions. So if you're familiar with IAM, this allows you basically to give specific individuals or specific instances API access to some AWS services. This is a very granular way to control permissions. And so this way you don't have to rely on anyone else's authentication. You can use the AWS authentication that you're already using and trusting in your applications. So we can add some existing or some pre-configured policies, but we can also custom build policies. So maybe, for example, I want to give everyone pull-only actions to this repository. It should be open. That's something you can configure pretty easily here. Let's check on our push. Remember, that was a 260 megabyte image, so it won't be immediate. And here you can see it's pushing the different layers of the image. So for every modification you make to an image with a Docker file, each one of those run commands, for example, builds its own layers, its own layer of the image. Next, let's take a look at the actual ECR or ECS console. Here I have a default cluster running, and everyone in their account has a default cluster already. It's just an empty namespace, but it's dynamically sizable. So I went through the first run wizard that you can do with ECS. If you go to the documentation and look at the first run wizard, it basically takes you through a console where you can select some options. You can choose things like the size of your cluster. You can choose if you want to deploy a demo app, and if you do that, it allows you to determine how many instances of it you should deploy. Should it create a service? Should it create a load balancer, et cetera, et cetera. So right now, we have 2 ECS instances running in my account. We can take a look at some vitals here. We can also see the version of the agent, the ECS agent that's running, and the version of Docker that's running. So we have the latest Docker 1.9 release. But to kind of support the notion that we mentioned earlier that these are your instances, you can take a look, and they show up just like normal EC2 instances under your account. They just also happen to be checked into a cluster, so you can interact with them via the ECS APIs. And so, looks like my image has finished pushing. So what do we have in this directory here? We have a sample task definition. So let's really quickly, let me grab this really quick. I'm going to need this. Do this the slow way because I'm not sure of how to paste from the clipboard using a Mac with Vim, unfortunately. So we'll delete this here. This is the image we're referencing earlier, which is the sample app, right? But now we're going to replace it with the image that we just built and pushed to Amazon ECR. So looking at the rest of this here, we can see that we're defining CPU, memory. It seems like a bit much. We probably don't need that much. We'll change that down a little bit. We're going to map container port 80 to host port 80, so we can hit it just over a normal web browser. And we can see that also we have a second container that's built here, which is just BusyBox on the back end. It's just a very simplified Linux distribution that has some core utilities really designed for containers. So the way this application functions is this BusyBox container writes the time of day to a file every second, and then our PHP app on the front end reads that time of day and displays it on the screen. So we can do two things here. One thing we can do is we can just do docker run p80 Amazon sample app. And then in my web browser, I'm sure everyone's going to do this now. You can see my application is up and running. But if I come back, Control C out of that, I can do the same thing. And it's no longer running. So now that we've told the task definition that we want to use this image, we can go ahead and register this task definition as being available. So we can use the CLI. What is my simple app task def.json? Oh, I see. My console's bugging out. Sorry about that. Okay, finally. Sorry about that. So now our task definition is registered. So we can go over here into the console, and we can look at our task definitions. You can see that we have a task definition here. We have my latest revision, which is 4. You'll have to trust me on that, but we just pushed that one. So you can see this is the registry we just created. The image is specified here using my registry. This is my demo app. We specified CPU and memory. And now we can actually do things with this container. We can deploy it to a cluster. So what do we want to do from this? I suggest, we create a service. We can choose the cluster we deploy it to. We can call it our demo service. We can start with just one task to make sure it works. And we can put that behind an ELB, which I've already created. And that ELB just happens to be running in the same VPC as my ECS instances. We're going to map it to port 80 on the container host, and then we're also going to specify the ECS service role, which basically allows ECS to do things on your behalf, like describe the load balancer, understand if the task has been checked into the load balancer properly, stuff like that. So we can create that service, and we can see that it's come up now, and we can watch events to see how the deployment goes. So right now we can see that we desire one of the tasks. We can see that we have 0 pending, 0 running so far. But as we give it some time to pull that from ECR, you'll see it change to 1 pending, and eventually we'll get 1 running. So let's look at the tasks that we have running now. We have 1. And we can see the direct link to it, so it's available here. But should also be available through our Elastic Load Balancer, right? So I have the EC2 Management Console over here. Let's look at my load balancers. We'll grab the A record, pop that into the browser. We can see we're hitting the same application. So should I need more capacity in this service, we can go ahead and modify that as well. So let's go back to the cluster. Let's look at my service. Click on this, and we'll go to update. Let's say we want 2. I can come down here to update my service. The update has been put into action, and we can see that we now desire 2. We still only have 1 running. We have to wait for the next container to deploy. And let's look at events. So it started my task. Let's see, do we have 2 running yet? And there we go. We have 2 running. Great. So ELB still responds. Looks like we're good to go. So in a couple of minutes, we went from basically source code in GitHub to a built Docker container. We pushed it to Amazon ECR to store the container. Then we told the task definition where that container now lives. It lives in ECR. Here's my repository. Here's the name of the image. And we took that task definition and we registered it with ECS. Once it was registered, we could take that task definition and build services from it, or deploy it to multiple instances in the cluster. So now we went from that one Docker container running locally on my machine to running across 2 EC2 instances behind an ELB, and it's ready to receive traffic. So that's about all I wanted to show in the demo here. We're doing pretty good on time. We have the required amount of time for Q&A. So let's take a couple of seconds here. Let's look and see what questions we have, and we'll be right back with some answers.
Great, thank you, Brandon. So audience, if you can take a moment to fill out the 3 poll questions to the left on your screen, your feedback can really help us improve our webinar programming. And also thank you, Daniela and Andrew, for answering the audience questions. Right now we have about 15 minutes till the end of our presentation, and we will start address some of the questions. Apologize in advance if we cannot get to every audience questions. You can still submit questions at this moment. I will give Brandon some time to review all the questions that's being assigned to him.
Okay, great. Now it's time to answer some questions. So let me see what we have here. So there's a really interesting question here. The first one that came up is, can you speak to the advantage of using ECS versus Elastic Beanstalk with Docker? And I think this may be one of the more common questions that I see about ECS. But here's the secret, and that's that the multi-container Elastic Beanstalk deployments actually are using ECS underneath, so some of the same primitives. So the advantage of using Elastic Beanstalk is really similar to using Elastic Beanstalk without containers, right? And that you have that awesome management overlay that gives you like a really easy way to manage all of your resources. And so if your web application happens to meet the paradigm that Beanstalk is best for, right? So you have probably a load balancer, some containers, maybe an RDS database in the back end, and you want to manage it all through the Elastic Beanstalk APIs, more power to you. We think that's a great option, and a lot of our customers feel like that as well. So I highly encourage that. Look at both. Generally, it comes down to how much flexibility and how much control over the underlying infrastructure do you need. If you need more control than Elastic Beanstalk allows you, in that you need more some unique architectures, then using a raw ECS API might be more to your speed. So it really depends, but I think both are great options. Another question here is, why do you need to specify memory for a container? So that's a really good question, but basically within the operating system, you need to tell Docker how much memory it should reserve for that one process. So memory reservations with Docker are kind of they're a static construct. So if you reserve 200 megabytes of memory for a process, that process will always have 200 megabytes of memory to work with. The counterpoint there is that CPU, for example, is a burstable construct. So you can define a very small amount of CPU for all of your containers on an instance and really oversubscribe your containers if you have kind of a burstable workload. But with memory, it always has to be a hard reservation. So this is actually a good way that you can scale your cluster by tracking how much memory reservation across your cluster you actually have currently. So if you know that you always need 200 megabytes of memory to place another task on an instance, you can scale when you reach less than 200 megabytes of available memory for reservation across your cluster. So I hope that answers the question. Let's see, what else do we have here? So there's a question about proxying connections to containers in AWS if you can't assign an elastic IP to it. So their suggestion was maybe use a NAT instance. So what you can actually do is you can definitely use an elastic load balancer to expose the containers to the internet, but those containers on their instances can live in a private subnet in the VPC. So long as your ELB can reach those instances in the private subnet, you can lock it down so that basically only the ELB can access that private subnet, and you don't allow direct connections to your containers or to your instances from the internet. A question is, what's the advantage of deploying my application using ECS as opposed to setting it up for Kubernetes to be run on EC2? I think the main thing to look at with ECS is that this really removes you from the responsibility of having to run cluster management software yourself. I've heard from a bunch of customers who decided to start using ECS that they didn't have time to teach their developers to maintain a cluster. They didn't want to have to teach them another paradigm to start working with a different cluster manager. So the advantage is that if you're already familiar with AWS, EC2 for example, or even if you're not, the set of APIs that ECS exposes are really straightforward, and it really alleviates a lot of the concerns you would have in terms of running a cluster management software yourself. And so I think that's the number one value proposition, is that we remove some of that undifferentiated heavy lifting from you. Question just in is, can you discuss service discovery options? I love talking about service discovery. So for those of you who are unaware, service discovery is basically the functionality that provides the ability for containers to find each other across a network. So if you have a front-end task and it needs to know some important information like where is my database, you can have a service discovery service that allows you to provide that information to different containers. It might be a key value store, it might be a distributed DNS system, but there's a bunch of different ways of doing that. Our two favorite right now, number one, in no particular order, they serve the function in different ways, but one is Weave, and so you can check them out at weave.works. And this is basically distributed DNS, and so you can reference containers by their container name across the entire cluster with no other work, basically. So once Weave is running underneath, it just allows you to make unqualified DNS requests to the container name, and Weave will route that across the cluster for you. Number two is Console by HashiCorp, and we're a big fan of Console. We actually use this in a boot camp at reInvent. And Console is it's a distributed key value store. Basically, it's like maybe sub-millisecond DNS, if you will. It has a REST and it has an HTTP and a DNS interface that allows you to pull information out of that key value store on the back end. Console definitely has more levers to pull. There's a little bit more complex configuration to get it set up, but it's a lot more extensible and it can do a lot of different things. So I would say, again, Console by HashiCorp and Weave. Take a look at those two. So there's a question about using a Docker Compose YAML file through the ECS CLI. Does this internally translate to an ECS task definition? The answer is yes. We do take a Docker Compose YAML file through the ECS Compose CLI and translate that to an ECS task definition. The coolest thing about the Compose CLI that we have is it's kind of like a 0 to 60 workflow experience, in that you can spin up an entire cluster from your Docker Compose file just from the CLI. And so it's a couple of commands to get a fully functional cluster up and running, because the CLI invokes CloudFormation behind the scenes, and it spins up the ELB, it spins up the instances, it can deploy the tasks to all the instances, it can create the service, you can use it to scale the service, and it can all be done just from your local desktop. There's a question about using EBS or EFS volumes in a task definition that will work on any container instance. So when you use EBS with ECS, in the task definition, you basically just specify what volume you want to expose inside of the container. And this gives you the ability to write data from the container to the underlying host. We've actually been in some discussions this morning about the best way to implement this because we've seen a couple of different approaches from customers. You can use EFS or NFS, and if there's a different provider for NFS, you can use NFS. If you need block level storage, you can definitely do EBS. And in some cases, customers are implementing aggregated block storage via iSCSI, for example, running like a cloud filer outside of their ECS cluster. So you have a lot of options, and maybe that's something that's very, very use case dependent. But certainly if you need to persist data, NFS, block storage, or S3 are all valid options. So the question is, how can we use the ECS scheduler to automatically store every log into a MongoDB cluster? And so I'm presuming that's for kind of some forensics retroactively on like what's happened on your cluster. The thing that I can tell you is that you can use CloudTrail to do a lot of this. I'm not sure exactly about the import process into MongoDB. I'm not exactly an expert in that, but we do give you the ability via CloudTrail monitoring to log every API call. And I presume somebody out there has exported it into a MongoDB cluster. So maybe we can follow up afterwards and talk about what that would actually look like. Very interesting. There's a question about secret management, which is always a fun thing to talk about. The question is, does ECS provide any support for having your Docker containers manage access to passwords, secret keys, etc.? The way that we address that right now in the documentation is that by using an IAM role that's applied to the instances in your cluster, that role can grant access to a specific S3 bucket, for example. And perhaps when your instances boot up, you can specify in the user data that the instance should grab that maybe a file out of S3 that can be encrypted, and they can pull that down to access the passwords or secrets that might be contained in that S3 file. There's also a bunch of other ways to do it through third-party tools. Actually, for example, you could use AWS KMS, but another popular option is Vault by HashiCorp, and that's a very popular secret management solution that you can definitely use with ECS. There's a couple of questions about auto-scaling your application. So there's a couple of different layers to auto-scaling in ECS. So underneath the cluster, your instances live in an auto-scaling group. And so you can scale based on typical EC2 metrics. It's also popular to scale based on things like response, like ELB metrics, like response latency, or maybe an SQS queue depth. But also you can scale the tasks based on a few different cluster aggregate metrics. So CPU load or memory reservation across the cluster or across a service are things that you can eject CloudWatch alarms for and then trigger a scaling action from there. All right, everyone. Hopefully we've got to your questions. If we haven't, we'll be following up afterwards to make sure everyone has been reached out to and that we've answered your questions. Thank you so much for coming. We hope you got something out of this. You learned a little bit about Docker or ECS. We encourage you to go forth, try Docker, try ECS. build some images, push them to ECR, deploy them to ECS. The instances underneath can be used in the free tier if your account is still in its first year, if you're using T2 micros. So you can also do it without any cost to yourself. Again, thanks so much for coming. Hopefully we'll see you next time. Have a lovely day. Take care, everyone.